Quantum algorithm is slightly different with the classical algorithm. Our bit of information is encoded using the superposition. And after that, we compute the system using the gate that can entangle and interfere this superposition state. So this is quite different, and I will start talking about, first I will talk about the superposition. The classical circuit use bit of information 0 or 1, light on or off. However, quantum mechanics allow to be two places at the same time, so we can do it better. Photon, let's look at the double slit experiment. So photon can pass through only upper path, which we represent 0 here. So I will say point it up because it's upper path, and it's 0. I just encode that up as a 0 information. And when it goes to the bottom path, I will rotate that arrow to be pointing down, and I will encode the information about the 1. But quantum mechanics allow that we can go both paths at the same time, so then I can have superposition state, which is not 0, not 1, it's a 50% chance of 0, 50% chance of 1. So I will rotate my arrow to the right and say this is superposition state. But there's also two different superposition states. I can either make a constructive interference, and I can either make a destructive interference. So I will say plus and minus, and I will rotate 180 degrees to represent the destructive interference. So we can say that it shows, so compared to the classical circuit, we only use 0 or 1. Now we have a more degree of freedom due to the superposition. In order to understand how to entangle and interfere that play the role in the quantum circuit, I think it will be easier to show actual example. So then I will introduce some of the quantum algorithm. Let's say we have a switch, and if it's a working switch, then depend on my input position, so 0 or 1, it will change the light bulb. It can be on or off. But if it's broken, whatever I turn it on or not, it will not respond to my signal. And there's two other cases that it will be always on, and it will not respond to my signal, even though I turn it on and off. And when you look at all the possible scenario, we have 4 different kinds of scenario. 2 broken case, then whatever my input is, it does not respond, and it's only give a 0 or 1. Or the working case, that it will respond to my input, so then it will be correlated output or anti-correlated output. So when I put 0, it will give a 1, or when I put 0, it will only give it 0. So here's the problem. Let's say we want to find what's inside of this box. There's 4 different types of switch can be inside, but we want to check sending a bit of information into the box, and we want to find that what switch is in the box. So let's say if it's working switch, and then working switch that is correlated output, when I put the 0 state as an input, it will not do anything, nothing to the second state. So can I tell that this is working switch by trial 1? No, because broken switch will give me same output. When I put 0, it will give me 0. So just by checking one time, I cannot really tell that this is working or broken. In order to tell this is working or broken, I need to prepare one more time with the opposite input state down and see that this flipped the second bit. So then I know that when it flip, then this is not broken switch, it is working switch. And this is a limitation of the classical computation, because we need to check all the possibility one by one. If we use the quantum computation, we can do it better. Let's say we prepare the state with the superposition state, which is either 0 or 1 at the same time. What happens when you put it into this superposition state into the circuit? Well, this is 0 and 1 at the same time, and my output will be depend on the 0 or 1. So when I put this circuit, actually the universe will split into 2 and give a flipping the bottom one or not flipping the bottom one. So then we have a 2 universe coexist at the same time. One universe have a up down, and the other universe have a down up. And this is entanglement, because when I measure the bottom qubit, it will decide which universe to collapse and then affect the other qubit to be change their state. What if we send both superposition state? we prepare like this and send it into the circuit, it will create something crazy. So let's say put it into this circuit. It will split the universe into the 4 because of when it is up, it will not flip, but also we can have a 0 or 1 because they're superposition. And my input state can be 1, then it will all flip, but also they have a 2 possibility. So then we have a 4 different universe. And this universe will destructively interfere each other. When you do the math, you will find that this whole 4 scenario will start interfere and collapse to one universe, which is that the top qubit will be rotated. So we can check that when we send this superposition state into this broken circuit, nothing will happen because of the constructive interference. However, when you put this superposition state to the working circuit, this will flip the top qubit because of the destructive interference. So just by simply measuring the top qubit, we know that this is working or broken just with one trial. So this is the advantage of the quantum computation. If you cannot follow detail, here's a summary. So quantum algorithm, first rotate the state to be in the superposition state, and then when you compute the problem, universe will split into 2 and entangle each other and interfere each other constructively and destructively and converge to one solution. And this is introduced by Dutch, and this is known as Dutch algorithm. As I have shown you that 2 qubit, we can see twice faster than speed of the classical computer. If the problem size increased, the normal computer will exponentially increase to the n to solve the problem. However, quantum computer only suffer the linear time to solve the problem. So we can say that certain problem, quantum computer can solve exponentially faster than classical computer. And he's the first person who discovered this quantum algorithm and first person to show that we have an exponential advantage. Now we have many algorithms. IBM have a lot of library of the circuit, have optimized the stock market, machine learning algorithm online. Since I'm an advocate for the IBM Qiskit, I want to advertise some of the feature. You can use the IBM quantum computer anywhere in the world. Let's say you want to program the molecular behavior, or make a vaccine, or optimize the portfolio for the stock market. Then you will use your laptop and your program and code like Python to program what you want to do. Qiskit have there is already a lot of library of the circuit, so you can use that to program it and send it to IBM quantum computer. Then it will calculate actual quantum circuit and give it back to you the result. So what can you do with the answer if you have a perfect quantum computer? If you have a perfect quantum computer, just with a 50 qubit, we can simulate whole human information. More than 200 qubit, we can simulate the entire observable universe. Think about it. Just with the 200 photon or atom, you can put it on your hand. It's even smaller, so then you can even see on your naked eye. It has exponential power to solve the problem. Currently, we do not have a perfect quantum computer because of the decoherence. As I mentioned, when you look at it, it becomes a particle. When we don't look at it, it becomes a wave. So if I say a little bit more accurately, which is that if we have any ability to extract the information out from the system, then even though we don't look at it, it can influence the state. So any vibration, any heat, any sound coming out from the quantum computer can influence the quantum computation. So because of that, if we can know the information, this will create the error on the quantum computer. So for this reason, we cannot isolate the quantum computer perfectly isolate from the environment. So that's why we try our best. I mean, IBM tried best to put their quantum computer inside of the fridge. So then it's cold, nothing will coming out. But because of the error, even though you make it really, really good, 50 to 100 qubit cannot do the work, cannot simulate the universe. So we have to increase the number of the qubit, but also have to reduce the noise of the quantum computer. Yet, we don't have a perfect quantum computer, but here's the most we are in the most exciting time in human history. This is something beyond any revolution human ever experienced. We are reducing the error and increasing number of the qubits exponentially. And this increased the power of the quantum computation exponentially. So just take a look how the computer revolutionized our society. We sent a person to the moon, designed a new drug, and predicting the weather. And if we keep growing our power of the quantum computer as rate is now, building quantum computer is just a matter of the time. And we might cure the disease, complete prediction of the weather, even control the weather, optimize, simulate the battery and solar panel so then we can solve the energy problem. I really hope, maybe, that we might answer some philosophical question of our life. Thank you for your time and attention.